Hi everyone, myself Jamsina P, Assistant Professor, PG Department of Mathematics from E-Content Development Center, Majlis Arts and Science College, Puramanur. Today we are going to discuss the topic Mobius transformation in the paper Complex Analysis, 3rd semester MSc Mathematics under University of Calicut. After watching this lesson, you can identify the Mobius transformation. You can able to find the inverse of Mobius transformation, also able to solve the problems related to fixed points. Now let us start with the definition of Mobius transformation. What is a Mobius transformation? A mapping of the form S of z equal to az plus b divided by cz plus d satisfying ad minus bc not equal to 0, where a, b, c and d are complex numbers, is called a Mobius transformation. Here the term ad minus bc is called the determinant of Mobius transformation, and in the case of Mobius transformation it is very important that the determinant should be non-zero. This transformation is introduced by the eminent mathematician Auguste Mobius. We have an example: S of z equal to 2z plus 3 divided by 4z plus 5. Here a equal to 2, b equal to 3, c equal to 4 and d equal to 5, and ad minus bc equal to minus 2. It is a non-zero number. Therefore, S of z equal to 2z plus 3 divided by 4z plus 5 is a Mobius transformation. Now we have the term linear fractional transformation. From the definition of a Mobius transformation, it is very clear that S of z equal to az plus b divided by cz plus d contains two linear transformations, az plus b in the numerator and cz plus d in the denominator. That is, a Mobius transformation is the fraction of two linear transformations az plus b and cz plus d. Therefore, it is known as linear fractional transformation. Next we have the inverse of a Mobius transformation. By the definition of Mobius transformation, we have S of z equal to az plus b divided by cz plus d. We can denote it as w, where ad minus bc not equal to 0. By cross multiplying, we get w into cz plus d equal to az plus b. By removing the brackets, we get w cz plus wd minus az minus b equal to 0. Taking z as common, then z into cw minus a equal to b minus dw. Therefore, z equal to minus dw plus b divided by cw minus a, or otherwise it can be written as dw minus b divided by minus cw plus a. By replacing w by z, we get dz minus b divided by minus cz plus a. Here it can be denoted by S inverse of z. Here also the determinant ad minus bc is non-zero, and this function S inverse of z equal to dz minus b divided by minus cz plus a is called the inverse of S of z. Now we have bilinear transformation. From the definition of a Mobius transformation, w equal to az plus b divided by cz plus d, where ad minus bc not equal to 0, it is clear that this transformation is linear in both z and w. Therefore, it is also known as bilinear transformation. Now we have to discuss about the group structure of Mobius transformations. The collection of all Mobius transformation form a non-abelian group under function composition. To form a group, a collection should satisfy certain properties. That is, if S1, S2 and S3 are three Mobius maps, then first we have the closure property. S1 composition S2 is again a Mobius transformation. Second one is associativity. S1 composition S2 composition S3 equal to S1 composition S2 composition S3. And identity map, S of z equal to z is the identity map in the case of Mobius transformation, and the inverse we already discussed. S inverse of z equal to dz minus b divided by minus cz plus a is the inverse. Now we have to check the commutativity. We know that the operation composition of functions is not commutative in general. Therefore, the set of all Mobius transformation form a non-abelian group under function composition. Look at the definition of fixed points. The points set satisfying the equation s of z equal to z is called the fixed points of s of z. And in the case of a Mobius map, s of z equal to z implies az plus b divided by cz plus d equal to z. By cross multiplying we get az plus b equal to cz square plus dz. Then we get a quadratic equation cz square plus d minus a into z minus b equal to 0. We know that a quadratic equation has at most two solutions. That is, if c not equal to 0, the Mobius transformation s of z has at most two fixed points. Here we have some more results about the fixed points of a Mobius map. Any Mobius map other than the identity map has at most two fixed points. Now what about the identity map? For the identity map s of z equal to z, every point is a fixed point. We can consider an example. Fixed points of s of z equal to 3z plus 2 divided by z plus 2. By definition, s of z equal to z implies 3z plus 2 divided by z plus 2 equal to z, and by cross multiplying we get the quadratic equation z square minus z minus 2 equal to 0. By solving this we get two solutions, z equal to minus 1 and 2. That is, z equal to minus 1 and 2 are the fixed points of the given Mobius transformation. Here we have some problems related to the topic. That is, first one, find the inverse of the Mobius map s of z equal to 4z plus 2i divided by z minus 1, and next about the fixed point, finding the fixed points of the following. First one, s of z equal to z plus 2 divided by z minus 1, and second one, s of z equal to 3z minus 2 divided by 2z plus 3. In this session, we discussed the definition of a Mobius transformation, inverse of a Mobius transformation, fixed points, and problems related to fixed points. I hope you have understood my class. Thank you.